All right. So in the 3.9 examples, first I posted just this general strategies. Related rates can be kind of tricky. Family. So, but if we follow the same structure all the time, it's going to be a little bit easier. And so, main thing you're going to want to do is draw a diagram. There's going to be a related rates question on test 3, but also on the final. And so drawing the diagram is going to be 1 mark, and then just kind of establishing what you need to solve for is another mark. And then, so even if you're not able to solve the problem, there's a lot of kind of part marks. I think it's out of 6 or something. So kind of a biggie, but there's lots of marks to be had, even if you can't get to the solution. So like drawing it out, figuring out what you need to solve for, and just kind of setting it up, doing your best. So I think today we'll go through, I like the ones that I stole from Steve. So I think we should go through 6, 7, and 8 today, because they're just kind of the 3 different varieties that we could have. And then you'll see that there's similar ones. We did question 1 last day when we introduced related rates, and then the others are similar to the ones that we're gonna do. So, okie dokie, artichoke. Just for a warm-up, I guess I should say, just as a kind of a review, kind of just a recap. We started related rates last day. And the main idea is you've got kind of the formal summary, but the main ideas of related rates are going to be that you want to find a rate. So want to find a rate. And then we're also given another rate. Given another rate, one that's typically easier, you know, to measure or something like that. And so what we do is we establish a relationship, I'll say a mathematical relationship. Mathematical relationship between the quantities in the given and the desired rates. Between the quantities in the given and desired rates. And once we do a couple of examples, you'll see. And then 10 minutes. You beat it by 1 minute, Cisco. Alone for the first 10 minutes. It was 9 minutes last time, I'm pretty sure. It might have been 14, but well, I feel like it was 9. All right. You and me both. Well, not really. Oh, gross. You're probably among the furthest. It's daylight savings. It's Tuesday. Who knows? For some reason, I'm awake in the mornings, but then when I wake up, my brain's like, no, you're supposed to be tired because we set the clocks forward. So then I'm like, oh, I'm so tired. But when I wake up, I'm like alert and awake. So I don't know what's going on. But my brain's like, no, you're supposed to be tired. So anyways. Oh yeah, so you establish some sort of mathematical relationship, and we use the formula for volume last day, and we'll see some other types of situations that we could, we'll look at the three kind of main different versions. Me too. And so that we'll see, and then you've got the other ones to kind of work through, and I'll post those solutions too. But the last thing that you want to do is use the chain rule to take the derivative. Use the chain rule to take the derivative. Right. Remember, a derivative is a rate of change. Well, that doesn't really say change, does it? The rate of change. And so that's where the related rates come from. I'll say, well, I guess I'll say now you will have your related rates. And then the last thing you do is you solve for the desired rate. So like I said, we'll go through and we'll do the three last questions on that handout. And if you're at home, the handout is on Moodle. So I'd say there are kind of, this is the first type of question that we could tackle. And so two things are either moving towards each other or moving away from each other. And we want to find the rate that they're moving towards each other or away from each other. And so, and then the second type that we could have is kind of like a street light one that we're going to do. And so street light or a flashlight, usually it has something to do with how the shadow moves. So as you move towards a light, how does the shadow, the rate of your height of your shadow, for example, change? If you move away from the light, how does your shadow change? And finally, we've got the conical cup, I guess. And so we can find the rate of change of volume, and it's always in a cone for some reason, but they love that cone. So, so we'll work through one of those. Either we're filling it with water or whatever, or it sprung a leak and now water's leaking out at some rate. So those are the main couple of questions that we could work through. So here we go. So the first one, we'll start with this one because I think it's the kind of the most intuitive to wrap your head around. So two ferries depart Tsawwassen Terminal at noon. I'm from Tsawwassen, so of course I stole this one from Steve. One ferry is heading west to Victoria at 12 kilometers per hour, and the other is heading south to Seattle at 16 kilometers per hour. I should probably tell them that there is no ferry to Seattle from Tsawwassen, but it doesn't, yeah, but it doesn't matter. How fast is the distance between them increasing at 2 p.m.? Okay. So remember, we've got our strategy. Of course, now we've read the problem carefully, kind of goes without saying. But now let's draw a diagram just to figure out what is what here, right? What do we know? And then establish some notation. So the first thing we're going to do here is, well, I know if I start here, right, I have to head west and south from Tsawwassen. Oops, spell my hometown wrong. It's saw, was, sent, and then the T goes to the front. Okay, so this ferry is heading to Victoria. So I'm going to call this ferry B. I don't know. How do you draw a ferry? Yeah. That would be a different type of question. But let's call this RB. My kind of weird looking ferry. And then we've got another ferry heading. Oh, I guess I shouldn't have drawn the, trying to only draw lines. Only because I want them on the same. I guess it's moving faster, so it's going to be longer. Come on. There. And this guy, let's see if I can draw. Nope, boat looks the same. Even though it's faster, it'll be a sailboat. Sort of. And this one's heading to Seattle. So these ferries are heading away from Tsawwassen, right? Both of them. And so direction is going to be important for these related rates problems, right? Because a rate can either be increasing or decreasing. And so we need to figure out if this distance is increasing or decreasing, right? And so the distance, and if we use just our XY coordinates, despite moving in the negative direction of X, right? If we call this our X and this our Y, just for simplicity's sake, despite moving in the negative direction, X is actually increasing, right? The distance between Tsawwassen and the Victoria ferry is increasing for the duration of the ferry ride. Right? And so what I want to do is I want to make a note here to myself that X is increasing. Same thing with Y, right? I'm moving further and further away, and so Y is also increasing. So these rates are going to be positive. And so what we can say is, well, I know that, where am I going to put this? I want it on the same page still, so I'll put it over here. dx dt, so the rate of change in X over time, so that's how fast we're going. And if X is the distance, then the first derivative is the velocity. And so we know dx dt, that's a rate, right, is 12 kilometers per hour, but I'm gonna ditch the units for a bit, make it easier to look at. But also we know dy dt, the change in Y over time, is 16 kilometers per hour. Fine, I'll put the units on. There. Although I find it gets a little bit confusing with the units, but I guess it's proper. Okay, so we've drawn a lot of it, but we haven't figured out what we're trying to solve for yet. So how fast is the distance between them increasing at 2 o'clock? So at a certain time point, right, we check in and see, okay, what's the rate of change? What's the instantaneous rate of change at this point, right? And so what we're trying to solve for is if we let this distance, we've got x, y, let's call this the hypotenuse or something like that, right? Just pick some variable that you know how to deal with, right? And so I'm going to call this the hypotenuse h. H is the distance between the two ferries. And so h is the distance between V and S, let's say. But we want to know how fast is the distance between them increasing, right? So what's the rate of their of that distance over time? And so we want to find dH dt at 2 p.m. So at 14 o'clock. Why do we care about that time point? Right? We could figure out in general how it's increasing, right? That's fine. But if we want an actual value, we need that time point. Okay, at this exact time point, I can evaluate this derivative dH dt. And what we can do, right, is at 2 o'clock, the two ferries have traveled for 2 hours, right? We know how fast they're going, so that's how I'm going to be able to figure out what x and y are. All right, so I'm going to sit on that for a little bit, but that's the reason that we need kind of that time point of where we're interested in. So I've got this presumably right angle triangle. It's not super clear, but it is a fair assumption, right? If one's heading west and one's heading south, there's no reason to think that it wouldn't be a right triangle. So how can I relate x, y, because I know those rates, right? I know dx dt, I know dy dt. How can I relate x, y, and h? Well, x squared plus y squared equals h squared, right? And so first thing you're going to do, and like I said, just doing this, if the question's out of 6, I want to say, 6 on test 2 or test 3, and it might just be 4 marks on the final, right? But there's related rates on test 3 and on the final, and so it's kind of a big deal. So on test 3, it's worth 6 marks, but just writing, like, having this, I'd say it's about 2.5 marks, right? So something for just sketching it out, figuring out what's going on, I'd say that's 1 mark, and just kind of establishing what we know is another mark, and then half a mark, just for good measure, I guess. 3 marks. Yeah. So even if this is as far as you get, right, you're still, you know, borderline passing this question. So it's not, you know, not unreasonable. Okay, so the next thing that we want to do, so this is where the work starts, right? And even this part might feel pretty good, right? So we want to establish the relationship. So the relationship between dx dt, dy dt, and h and dh dt, right? Relating x, y, and h is going to be x squared plus y squared equals h squared. So we have to establish that relationship. And then what do? We use the chain rule, right? So here we want to find a rate, dh dt, and we have another rate. We have actually two more rates, dx dt, dy dt, and then we establish a mathematical relationship between the quantities in the given and the desired rate. That's what we just did, right? X squared plus y squared is h squared. And so now we're going to use the chain rule to take the derivative, and now we'll have an equation that relates these rates. So breaking it up, we can say, okay, well then our related rates, if I'm taking the derivative of these things with respect to time, right, because I want dh dt, there's no t here. And so what I have is I can take, this is implicit differentiation, right? And so we get 2x dx dt, assuming x is a function of time. And then same thing for the y, 2y dy dt. Which is equal to 2h dh dt. This is how you're always going to take these derivatives, right? Because unless you have an explicit t in there, you have to multiply it by whatever the variable is, whatever the variable is with respect to time, right? And so the x squared becomes 2x to the 1, but I've ditched that, times dx dt. But notice that we know dx dt, we know dy dt, and we're trying to solve for dh dt, right? So everything's kind of falling into place here. We're solving for, I guess I should say solving for dh dt. We know dx dt, and we know dy dt. We can also find x, y, and h, right? So here, x, y, and h, after 2 hours, right, from noon to 2, we can find x, y, and h. So x is going to be, x is moving at 12 kilometers per hour. And so we've got 12 kilometers per hour times 2 hours. Puts me at 24 kilometers. Same thing for the y's. Y is moving at 16 kilometers per hour times 2 hours. I get 32 kilometers. And then h, well, we can start with h squared is x squared plus y squared. So 24 squared plus 32 squared. Let's see here. 24 squared plus 32 squared. So h is going to be the square root of 1600. So h is 40 kilometers. And we already know, I'll highlight this, right? dx dt, oops, dx dx. dx dt is 12, and dy dt is 16. So now, right, if we solve for dh dt, we have to divide both sides by 2h. We've got that common 2, but I'll just show explicitly. If you wanted to just cancel it, that's fine. So now we can establish that, so I don't have to scroll around so much. 2x dx dt plus 2y dy dt over h is dh dt. Oh, 2h. Sorry. Whether you cancel those 2's or you keep them, it doesn't matter. I'm going to pull out that common 2 so I don't have to deal with it. So kind of revolving door, I like to have whatever I'm solving for on the left-hand side. So dh dt is going to be x, which is 24, times dx dt, which was 12, plus y, which was 32, right? Yep, 32, and dy dt is 16. All over h, which we just said was 40. So 24 times 12 plus 32 times 16, 800 divided by 40, I get dh dt is 20. Kilometers per hour, right? Because it's a rate of change. So kilometers per hour, mostly because all the other ones have been in kilometers per hour, but also if we worked out the units in dh dt, we would get to kilometers per hour. So therefore, right, remember when we're talking about rates, we have to establish if the rates are increasing or decreasing. And so here, thinking back to just kind of logically, if these 2 points are starting at the same point, or these 2 values or ferries, I guess, are starting at the same point and they're moving in opposite directions or kind of away from each other, right? Then the rate that they're increasing, the distance is changing between them is increasing. I couldn't even say it without saying it. But so it'll be obvious whether it's increasing or decreasing. What's not obvious is that you have to think about it, but it's just something that you need to kind of remember. And so therefore the distance between the ferries, oops, is increasing at 20 kilometers per hour. Oh. Nice. Any questions about that one? No. So that was question 6 on here. If you have a read through the other questions, question 2 is similar. It's not exactly like it, but pretty well. It has one less variable, I would say. And then question 4 is similar as well, right? So now 2 cars are heading towards an intersection and we're basically finding the exact same thing. Right? So I don't know what to call that type of question. 2 things approaching or moving away from each other, right? Just kind of in a triangle type of situation. If we go to question 7, we've got a different type of problem. Although it ends up being, very similar, they're all related rates problems, so at the end of the day, they'll be very similar. Okay, a straight light is mounted on top of a 15-foot tall pole. So a man 6 feet tall walks away from the pole at 5 feet per second in a straight line. We can assume that it's a straight line even if it didn't say, only because it'd be really tricky if he was kind of walking like this. So we can just assume that he's moving in a straight line. How fast is the tip of his shadow traveling when he's 4 feet away from the pole? So 40 feet, I guess, not 4, 4t. All right, so first thing we're gonna do is we're gonna sketch this thing out and try to get a handle on what's going on here. Okay. And so let's start over here. I'm told that there is a street light here. My kind of not very good street light there. And what else are we told? It's on a 15-foot tall pole. So I know that distance is 15. A man who's 6 feet tall walks away from the pole at 5 feet per second in a straight line. And so here from this pole, I can walk all the way out in that direction. So this light, the trick with these light questions is just kind of draw a line that kind of goes down at some angle. Sometimes we have to care about the angles. I haven't picked any questions like that, so but there are questions like that where we incorporate the angle, but then it's just SOHCAHTOA, so it's not, nothing crazy. But here, 40 feet away, we've got this man. Oh, I guess I should make it so he's walking. He's not just standing, he's on the move. I'm not a very good drawer. Woohoo. So, here's our guy. We're told that he's 40 feet away from the pole. And so, where does that? Looks like we don't actually, I don't know. Who knows? Let's map it out and see what happens. Anyway, so one thing that we are going to use quite a bit are similar triangles, right? And so knowing what this big triangle looks like, we also see that there's a triangle here. All right. And so we've got this similar triangle. Similar triangle. So we'll end up using that in the next part or in the next question as well. So we'll kind of keep that in mind. And so, and we're told that this guy, he is 6 feet tall. All right. For some reason, and I just kind of stole these notes from Steve, so that's why I don't know why he hasn't put 40 here, but let's just follow what he did, and he knows what he's doing. It's only because I didn't want to use the examples from the textbook for these ones, because those are the ones at the top. So those are the ones that they walk you through in the textbook. So I wanted to steal some other ones, but here we go. So if we let that distance be A between the pole and the guy, then, and we let this distance, overall distance, be B, then this distance here is going to be B minus A. Just chipping away at B minus A. Okay. The shadow is going to be from the guy all the way to the end of the light shining, right? And so the shadow, let's say, is somewhere all the way along here. Okay, so this guy is moving at 5 feet per second. And so he's moving away from the pole at 5 feet per second. And so he's chipping away, where he's increasing the distance of A at a rate of 5 feet per second. And so what we're told is that dA dt is 5 feet per second. Is that fast? I feel like that's fast. Yeah. Even then, I'm not entirely sure how far 5 feet is, but feels like a long distance to go in 1 second. Anyways, doesn't matter. I'm sure it's okay. Yeah, he's sprinting away from the pole. So we want to know, how fast is the tip of his shadow traveling when he is 40 feet away from the pole? And so, well, I guess maybe the shadow doesn't go the whole way out. He's not that tall, like that. So what we want to find is, we want to find, hey, dB dt, it says. Tip of the shadow. Let's just go with it. We want to find, I'll even do it in a different color. Find dB dt. Okay. Probably do another one of these. I don't think I love this one. But anyways, we'll just do it. Okay, so let's say we want to find dB dt. Sorry guys, I don't love this one. Let's establish the relationship first. And one thing to keep in mind, right, that we said is that we're going to use similar triangles for these. Similar triangles. And so the key is that 15 is to B as 6 is to B minus A. So 15 is to B as 6 is to B minus A. And if the goal is finding dB dt, and I know dA dt, then that's a pretty good relationship to have. So now I can cross multiply and I get 15 times B minus A is 6B. So I get 15B minus 15A is 6B. 15 minus 6B makes 9B, which is going to be 15A if I move it over to the right-hand side. So that's our relationship, how A and B are related. And then what we do, the next step, right, is we use the chain rule to find the related rates. And so taking the derivative d dt, right, the derivative with respect to t on both sides, we get 9 dB dt. Right? The derivative of 9b with respect to b is 9, but then we have to multiply it by dB dt. Same thing on the other side, we get 15 dA dt. But then, and just to have it all on the same page, I just need one more line. dB dt is 15 times dA dt, but we know dA dt is 5, and then divided by 9. Maybe I needed another line. Anyways, 15 times 5, and it was increasing, so it's positive divided by 9. I'll just do it here. 15 times 5 divided by 9. 8.33, repeating. So approximately 8.33 feet per second. Just to keep it on the same page. We can do the other light problem 1. Let's do, yeah. See if I have it. Have it worked out from before. I know I said we weren't going to do 5, but I'll just erase that and then no one will know. Just for a better light one, let's do 5 as well. That other one, I don't know. I'll have to ask Steve what's going on. Unless it makes sense to you. But to me, when I read it, the tip of the shadow, I'm not sure how that's B. Unless B only goes to the tip of the shadow, then it makes sense. Maybe it only goes to the tip of the shadow, like so. then this distance is going to be b minus a. Well, where does the shadow go until the tip of the triangle? If you've got light coming here, I guess maybe it goes till the tip. Maybe I don't know enough about shadows. Maybe that's the problem. To solve this problem on my own. I think it was right the first time. B minus a. And I think the shadow, let's make the shadow go all the way. I just don't know enough about shadows, I guess. Anyways. Let's do question 5 for hopefully a better one. Okay. First thing we want to do, right, is, well, read the problem. So a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so you've got a guy and he's walking along a path, right? And somewhere down here, you've got a searchlight and it's just going to follow him. And so it's rotating at some rate. So let's sketch this out. So first we'll start with our path. And the searchlight is a searchlight is located on the ground 20 feet from the path. And so here, I've got this searchlight down here. And I'll put it at a right angle because there's no reason to think it's not. And here, that's 20 feet away. And the guy is walking somewhere here. He started presumably on the path and he's right above the searchlight. And then he's moving out this way in this direction at 4 feet per second. If we let this distance be x, x is increasing, right, because we're moving away from the point. And so x is increasing. And so 4 feet per second is the rate that it's increasing, so it's going to be positive. And what else can we jot down here? Well, the angle that it's rotating at, let's say here, let's call this just theta. So what we're told in kind of a sneaky way, so at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Just by, we know the hypotenuse is always going to be longer, right, than I guess the adjacent in this case, right? And so here, this is the point closest to the searchlight. is this point here. So when x is 15, right? So at what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? What this is saying is that x must be 15. I'm going to keep it as x for a little while longer. We don't want to plug in values too soon, because notice that we've got dx dt is 4 feet per second. And so unless I can take the derivative of x with respect to t, which I can't do if I just plug in 15 right away. And so I want to keep and be able to plug in dx dt later on. So, so that's why I'm going to keep x as a variable, even though I'll be able to substitute x equals 15 in later. And so we want to find the rate that it's rotating. So d theta dt when x is 15. Okay. So I can relate x and 20 and theta, right? Because I know from SOHCAHTOA, I know that if theta is the angle and I've got the adjacent and the opposite, right, then I can say that by SOHCAHTOA, we can find the relationship. It's more to establish where I got these things from, although it might be obvious. SOHCAHTOA says that, okay, the tan of theta is going to be the opposite x over the adjacent 20. And so we've got tan theta is x over 20. Just to make this a little bit easier, I'm going to move the 20 over to the left-hand side. So then I get 20 tan theta is x. So that's going to be our relationship. You could definitely keep x over 20 if you wanted to, but just makes it easier to deal with. So now we want to find the related rates, which means we have to take the derivative of both sides with respect to t. So we've got the derivative of tan theta, which is going to be 20 secant squared theta d theta dt. There's no explicit t in there. And then on the x side, we've just got dx dt. We want to find d theta dt. So solve for d theta dt. So we get d theta dt is dx dt divided by 20 secant squared theta. Okay. So we know dx dt. I don't have a secant squared or even a secant button. I don't know. And so I'm going to have to use some sort of identity, but 1 over secant squared is cos squared. So And I think I've said it before, but if there is kind of an obscure identity that you'll need to know before a test, I'm going to let you know. Okay. There are a few that I expect you to know. Cos squared plus sine squared is 1, for example. That's one that I definitely expect you to know. But any other identities like this one, I would consider a little bit obscure. But if you use it enough, then you probably would remember it anyways. So this is going to be 1 over 20 cos squared theta dx dt. So we get 1 over 20. I know dx dt, but I actually don't know theta quite yet. But I can put in dx dt now because I have differentiated x with respect to t. So I'm out of the woods. So I've got cos squared theta times dx dt, which is a positive 4. So that leaves me with 1/5 cos squared theta. We still need to find theta when x is 15, right? Because remember, that's another thing that we were given, right? That's the time point that we want this thing at. So we want to find d theta dt when x is 15. When x is 15, tan theta is 15 over 20. Let me use cos, but when x is 15, tan theta is 15 over 20. Let's make sure I get the same numbers as on here. I've got something slightly different, 15 over 20. And then, so theta is going to be the arctan of 3 over 4. Inverse tan of 3 over 4. How come that's not working? Inverse tan of 15 over 20. Get the same thing. Okay, fine. I'm going to put this over here and we can dissect it later. See why it's not. Do you guys see why that's not working? 15 over 20. Well, I guess you need to know what I've got on here. And I stole this from the textbook, so that's why I'm doubting what I did there with the tan theta. So when x is 15, the length of the beam is 25. Let's just check that out. We've got 15, 20. And so 20 squared plus 15 squared is 625. Okay, we're on the right track. Root 625 is 25. So cos theta, oh, it's because we're not solving it. Oh, okay, it would probably work. Okay, so cos theta is going to be, and here's theta. Cos is adjacent over hypotenuse, so 20 over 25. Cos theta is 20 over 25, which is 4 over 5. The reason they wanted cos is because we've got the cos squared. And so d theta dt, therefore d theta dt is going to be 1 over 5 cos squared theta. And cos squared theta is just So 1 over 5 times 4 over 5 squared. So 1 over 5 times 4 over 5 squared. I get 16 over 125, which is 0.128. Let me just move this and see if we solve for theta, right? That's another option that I was about to do. And I started doubting myself. Trust your gut. Or let's see if we can do this. Right, so one thing is to figure out, okay, what's cos theta, and then just square it, and then I've got the solution. What's another way? If we could find theta, then I can plug theta into the cos squared theta, and I should end up with the same result. Right? So let's just try solving for theta. So I get the tan inverse of 3 over 4. Theta is, it is approximately 0.6435. I'm going to keep, of course, all my decimal places in here because I want to do, so therefore, d theta dt is going to be 1 over 5 cos squared of 0.6435. Okay. So the cos of that, and then square that, and then divide it by 5 does put me at the same thing. So let me just save some space here. Oh. D theta dt is 0.128. So it works out to be the same thing. What a relief. Couldn't have two things not work out. Okay, so same procedure for all these, right? Even though they're kind of tricky to map out, usually once you've got them mapped out and figured out what you want, then it'll just kind of fall out. So let's see here, we did 5, 6, 7, let's do 8, and that'll be our last one. I was worried just the 3 questions would take all class or more. Turns out we had a little bit more time. Next day, what I want to do is I want to do 310, which is linear approximations, which is way more fun than related rates. It's just easier kind of to think about to do. So linear approximations, but then also a little bit of review for test 3, right? Because test 3 is on Tuesday. And so, because we won't do the review before the test. So that's why I wanted to kind of make a little room on Thursday for some review. Okay. The last thing on the test, it is either, I think it's a related rates problem, but linear approximations are on there too. So do you mean physically on the test or the last topic on the test? Linear approximations. Yeah. So from next day. Yeah. And that's the end of chapter 3 that we're doing, 310. And then we're into chapter 4. And all of a sudden it's over. That's crazy. So just like always, I'll give you guys a breakdown of the test, and then we'll go through some review problems. You'll be all good. Okay, so the third type of problem, I love these conical funnels or just cone-shaped whatevers. For some reason, I think because the volume formula, it just lends itself to related rates for cones. And so just love these cone problems. So let's do a cone problem. A conical funnel has a diameter of 10 centimeters at the top and a height of 12 centimeters. So what does this thing look like, right? If we're talking about a conical funnel, then I'll just kind of draw it like this. And we can assume that these sides are straight, actually. So let me just make that clear here. There. So we have a diameter of 10 centimeters and a height of 12 centimeters. Water flows out the bottom at 5 centimeters cubed per second. When the hit height, a little too speedy. When the height of water is 6 centimeters, how quickly is the height of the water falling? Okay, so we've got this kind of hypothetical height, h. And what we can do is we can split this thing up and talk about similar triangles, right? Because we've got this right angle here. And if I know that the diameter is 5 centimeters, then I can also say that the radius, or sorry, the diameter is 10 centimeters, the radius is 5 centimeters, and then we can call this just the radius r. So if we just break it down and look at half of this cone, right, then we'll be able to figure out, okay, I can figure out what r is in relation to 5 if I know how h is related to 12. And so here, if I've got some water in here at this point, we're told that the water flows out the bottom at 5 centimeters cubed per second. And so dV dt is 5 centimeters cubed per second. One important thing is that this is going to be decreasing, right? Because it's decreasing, so it's flowing out the end, decreasing, right? And so here we can kind of show the water coming out of the funnel at a rate of 5 centimeters cubed per second. And so what we want to know is when the height of water is 6 centimeters, how quickly is the height of the water falling? So we want to figure out, so what we want to find dH dt, the rate that the height is decreasing, right, with respect to time, when h is 6. So we're talking volume, volume of a cone, and so we need the volume of a cone. Volume of a cone is going to be, the volume is 1/3 pi r squared h. Again, I'm pretty sure if you need something like this on the test or on the final, right, we would give it to you, or I would at least. It's good to know these things, right? But in a test situation, we all blank, so. The volume is 1/3 pi r squared h. We've got the volume, we've got r, and we've got h. We really only want these in terms of just two variables, right? We know dv dt is 5, -5, and we know dh dt is the one we want to find. And so the one I'm not really interested in keeping is the r. And so we can rewrite this by replacing r with a function of h. Okay, so how are we going to relate r and h? Well, I can use similar triangles again. Right, so here we go again, because I know h is to 12 as r is to 5. Right? And so I can use these similar triangles. So by similar triangles, we said that 5 is to 12 as r is to h. So I can cross multiply these things or even just solve for r. So r is going to be 5h over 12. Okay. So now I can write that the volume is 1/3 pi, and then r squared is 5h over 12. So squared, 5h over 12 squared, and then times h. So now I've got volume is 1/3 pi times 25 over 144 h to the 3. So this is the relationship. I'll put that up here. The relationship is that v is 1/3 pi times 25 over 144 times h to the 3. And so now I can find the related rates by taking the derivative with respect to t. Take derivative with respect to t. So I get dv dt is 1/3 pi. Those so far, all these are constants. 1/3 pi 25 over 144 times, and then the derivative of h with respect to t is going to be 3h squared times dh dt. I'm trying to solve for dh dt. So solve for dh dt when h is 6. When h is 6. So solving for dh dt, I can simplify a little bit. Right? For instance, I can cancel this 3 and this 3 because they're all being multiplied. But beyond that, I'm not really able to do anything else, right? And so, but I can solve for dH dt. So dH dt is going to be dV dt, kind of keeping it on one line, divided by 25 pi over 144 times h squared. Just kind of fraction over a fraction. I get 144 over 25 pi h squared times dV dt. Flip and multiply. dH dt is going to be 144 over 25 pi. H is 6, so 6 squared times -5, right, because it's decreasing. So I get -144 times 5, -720 divided by, and then 6 squared times 25 divided by 900 pi. 720 divided by 900 simplifies to 4 over 5, so I get -4 over 5 pi. So if I do -4 divided by 5, oops, bracket 5 pi times pi, oops, there. I get roughly -0.2546479089, or if we're rounding to, let's say, 3 decimal places, -0.255. And the rate, right, is going to be centimeters per second. Any questions about that one? No. Not a one. Okay. Then what I'll do is, because I think it's enough of me blabbing at you, I'll post the solutions to the remaining ones, but I'm pretty sure all the remaining ones are actually just in your textbook, but I've got them, so I may as well just post them. Have a work through those ones and then check your work, right, just to see, just for extra practice. And then that's it. Related rates. Big topic. Done and dusted. Any questions? No. All right. Then I will end this. Bye, guys. Make sure everything was good.